Welcome to all. Our today's topic is thin-walled pressure vessel. Pressure vessels are closed structures that carry high pressure fluids or maintain vacuum inside them. That is, say this is a pressure vessel. It carries high pressure fluids. So this is high pressure fluids. And say fluid pressure is P, and atmospheric pressure outside is atmospheric pressure. Atmospheric pressure is P atmospheric, where P is greater than P atmospheric. So this is one type of pressure vessel. Another type of pressure vessels can maintain vacuum inside them. That is a closed structure. This is a pressure vessel, and inside it there is a vacuum. So it can maintain a vacuum inside it. That is here P atmospheric, and vacuum pressure means this pressure tends to 0. So here P atmospheric obviously greater than 0. And examples of pressure vessels are boilers, tanks, pipes, etc. When it carries high pressure fluids, it is classified as internally pressurized vessel. Why? Because P is greater than P atmospheric, so net pressure force will act along this direction. So from pressure is coming from inside direction. So this is internally pressurized vessel. So when it carries a high pressure fluid, that is called internally pressurized vessel. And when it maintains vacuum inside it, that is net pressure force P atmospheric is greater than 0, that is it will act like this. So P atmosphere will act like this on the vessel. So this is called externally pressurized vessel. This is called externally pressurized vessel. So this is internally pressurized, this is externally pressurized. So there are two types of pressure vessel which can carry high pressure fluids are classified as internally pressurized pressure vessel, and when it maintain vacuum inside it, it is called as externally pressurized vessel. Pressure vessels are considered to be thin walled. Our objective here to study on thin walled pressure vessel. So when a pressure vessel will be called a thin walled pressure vessel? When the ratio of internal diameter, that is di, to thickness ratio is greater than 20. If internal diameter to thickness ratio is greater than 20, it will be called a thin walled pressure vessel. The radial stress in thin walled pressure vessel is quite small compared to tangential stresses. So what we have noted, that is radial stresses is quite small compared to tangential stresses. Now what is radial stress and what is tangential stress? Let me explain through a schematic diagram. That is, say this is a pressure vessel. So there are three directions, three mutually perpendicular directions. Say this is direction 1, that is 1 indicates longitudinal direction. Longitudinal direction. This is direction 1. Direction 2 is circumferential direction. Circumferential direction. And direction 3 is radial direction. That is, which is perpendicular to 1 and 2. So direction 3. That is, so along 3 the stress is called radial stress. So radial stress is nothing but sigma 3. That is along direction 3. That is the radial direction, which is perpendicular to this surface element. Say surface element, small element is A, B, C, D. So radial direction is perpendicular to this face ABCD. So this is mentioned that radial stress in thin wall pressure vessel for thin wall pressure vessel is quite small compared to tangential stresses and can be neglected. So the radial stress is along direction 3, that is we can also notice we can also call it sigma 3. So sigma r is sigma 3 because this is along direction 3, that is we can neglect it, that is 0 compared to tangential stresses. And what are the tangential stresses? Tangential stresses acts along 1 and 2. So sigma 1 and sigma 2 are tangential stresses. Longitudinal stress is noted by sigma 1 and sigma 2 is circumferential stresses, and they are tangential stresses. Why tangential? Because they are tangential to this surface, they are tangential to this surface, and sigma 3, that is the radial stress, is normal to the surface. So 3 is normal to this surface, and 1 and 2 are tangential. 1 and 2 both are tangential. Okay, so compared to tangential stresses, radial stress is quite small and can be neglected, that is sigma 3 or sigma r is 0 for thin walled pressure vessel. For thin walled pressure vessel, next point, the tangential stresses are considered uniform throughout the thickness, and this type of stresses are known as membrane stress. Let me explain this also. This was the pressure vessel. Say this was the pressure vessel. This is the longitudinal direction. This is the longitudinal. This is circumferential direction. So this is direction 1. This is direction 2. And this was direction 3. Now, if I call it ABCD, this small element, if I call it ABCD, and here I am drawing the enlarged view of ABCD. This is the enlarged view of ABCD. Sorry. This is the enlarged view of ABCD. So this is the thickness. Say this is the thickness. So this is the thickness of the vessel T. Now what are tangential stresses? Sigma 1 acts along this. So this is sigma 1 and sigma 2 acts along this. That is, both sigma 1 and sigma 1 and sigma 2 are tangential to this surface ABCD. Tangential to this surface. So they are called tangential stress. So sigma 1 and sigma 2 are called tangential stress. And for thin wall pressure vessel, tangential stresses are considered uniform throughout the thickness. That is, let us come to this figure. Along thickness, this is the thickness, this is the thickness. Along the thickness, sigma 1 is constant. So sigma 1 is constant, and such type of stresses are called membrane stresses. Membrane stresses. When tangential stresses are constant throughout the thickness, it is called membrane stresses. And we have already noted that along 3, that is the perpendicular to this surface, sigma 3 is 0. Sigma 3 is 0. So we can omit this. So there will be no sigma 3, only tangential stresses, that is sigma 1 and sigma 2. Sigma 1 is along longitudinal direction, that is called longitudinal stress, and sigma 2 is along circumferential direction, that is called circumferential stress or hoof stress. Now, how to calculate the value of sigma 1 and sigma 2? That is, if internal pressure is P, that pressure force will act along this direction, and say length of AB, length of AB is ds2 and length of AD is ds1. Before that, I have to mention another points also, that is this is R1. R1 is radius of curvature along longitudinal direction. This is center of curvature for longitudinal direction. This is C2 and this is R2. And this angle is theta d theta 1. They are small angle. This is d theta 2 because ABCD is a very small section, so this angle d theta 1 and d theta 2 will be also very small. Now let me define what is R1. First write down R1. R1 is radius of curvature, radius of curvature along longitudinal direction, null direction, along longitudinal direction, radius of curvature along longitudinal direction. This is the longitudinal direction and that is the radius of curvature along longitudinal direction. Similarly, R2 is radius of curvature along circumferential direction. Circumferential direction. C1 and C2 are center of curvature. Center of curvature. Okay. And what is sigma 1? Sigma 1 is longitudinal stress. And sigma 2 is circumferential stress, shear stress or hoop stress. So R1 is radius of curvature along longitudinal direction. R2 is radius of curvature along circumferential direction. Sigma 1 is longitudinal stress. Sigma 2 is circumferential stress or hoop stress. Now, if length of AB is ds2 and length of AD is ds1, then pressure force on this element, the net pressure force on this element ABCD is what? P into ds1 ds2, and that will act outside direction through the center of gravity of this element ABCD. So this is the direction of pressure force. Now this pressure force at equilibrium, this pressure force is going to be balanced by these internal resistive forces or these stresses, that is sigma 1 and sigma 2, that is components of sigma 1 and sigma 2 opposite to this force, that is along this direction. This is opposite to pressure force direction, will balance this one, that is component of sigma 1 and sigma 2 opposite, that is this green direction opposite to pressure force, will be same with P ds1 ds2. Now our objective is to determine sigma 1, that is the longitudinal stress, and sigma 2, that is the circumferential stress or hoop stress. To do that, let me draw this enlarged view of the element ABCD once again. Sorry. So this is the T is the thickness of the vessel. Radius of curvature along longitudinal direction is R1. Radius of curvature along circumferential direction is R2. Center of curvature along longitudinal direction is C1 and center of curvature along circumferential direction is C2. So this is the element A, B, C, D, and we have noted that this is sigma 1, this is sigma 2, sigma 2, and this is sigma 1. Sigma 1 and sigma 2 are tangential to the surface ABCD, and sigma 1 and sigma 2 doesn't vary along the thickness doesn't vary, so we consider that they will act along the mid layer. So they will act along the mid layer. This red one is the mid layer, and sigma 1 and sigma 2 are acting along the mid layer. Now, how to determine the value of sigma 1 and sigma 2? We shall apply equation of statics, because at equilibrium the force due to pressure, that is here we consider that internal pressure is P. Internal pressure on the vessel is P. So if internal pressure is P, and if we consider that AB was ds2 and AD or AD equal to BC equal to ds1, and AB and DC are same, DC equal to AB equal to ds2 and ds1, and we have also noted that this angle d theta 1 and this angle was d theta 2. As this element ABCD is very small, so d theta 1 and d theta 2 are also very small element. Now if internal pressure is P, then pressure force acting on the vessel will be along outward direction, and that amount is P ds1 ds. So this pressure force will be balanced by what? Balanced by sigma 1 and sigma 2. So this is the direction of pressure force, which is outward from the center of curvatures. Now the component of sigma 1 and sigma 2, which is towards the center of curvature, that will be same with this. So first we'll take the component of sigma 1 and sigma 2 along towards C1. That is, let me draw this view. We will see from this direction what we will get. If we take the projection of this direction, we will get this view. That is, this is A, this is D, and let me join them. Sorry, let me draw it once again. So this is C1, this is R1, and on this face sigma 1 is acting. Sigma 1, this is sigma 1. Sigma 1 is stress. Now what is the force? Force is stress into area. The length of AB is ds2, so, and thickness is T, so force will be ds2 into T. Sigma 1 ds2 into T. So this is the force. Now this angle is d theta 1. This angle is d theta 1. So this angle will be d theta 1 by 2. Similarly, this angle will be also d theta 1 by 2. Now, component of sigma 1 ds to t along this direction, that is towards C1, what will be the component? That is, there are 2 sigma 1 ds to t, so 2 sigma 1 ds to t into sine of d theta 1 by 2. Now, if d theta 1 by 2 is very small, then sine d theta 1 by 2 is nothing but d theta 1 by 2. If d theta 1 by 2 is very small, then sine d theta 1 by 2 is very close to d theta 1 by 2. d theta 1 by 2. So that is 2 sigma 1 ds2 t d theta 1 by 2, which is equal to sigma 1 ds2 t d theta 1, that is sigma 1 ds2 t ds1 ds1 by r1. Another point is that AD is ds1. AD is ds1. That is what? ds1 is nothing but r1 d theta 1. r1 d theta 1. So the net force towards C1 due to sigma 1 ds2t is this amount. That is sigma 1 ds2t ds1 by r1. So this is the net force. I am writing it once again. That is limited space here. So let me write down it here. Sigma 1 ds1 ds2 t divided by r1. So this is the force due to sigma 1 stress, that is sigma 1 ds1 ds2 t divided by r1. Now we'll compute or we'll determine the resultant force due to sigma 2. To do that, we'll take a projection along this direction, and what we will get, let me draw it here. That is, so here this is A, this is B, this angle is d theta 2, this angle is d theta 2, this is C2, this is R2, and on this face forces are what? Forces are sigma 2. Sigma 2 is acting along this direction, so sigma 2, and force is, this length is AD is ds1, so ds1 into t is the thickness, so ds1 into t, and here similarly sigma 2 ds1 t. Now similarly the component towards C2, this component, what will be this component? What will be this component? Before that, this angle, similarly this angle will be d theta 2 by 2, and here also this angle is d theta 2 by 2. Now this component, what is this component? What is this component? Let us calculate what is this component. There are 2 sigma 2, so let me write down it here. 2 sigma 2 ds1 t ds1 t sine d theta 2 by 2. Now let us compute this in the next page. 2 sigma 2, what was the value? 2 sigma 2 ds1 t sine of d theta 2 by 2 d theta 2 by 2. that is equal to 2 sigma 2 ds1 t d theta 2 by 2. As d theta 2 is very small, so sine of d theta 2 is nothing but d theta 2 by 2. That is sigma 2 ds1 t d theta 2, which is equal to sigma 2 ds1 t ds2 by r2. That is sigma 2 ds1 ds2 t by r2. So due to sigma 1 that stress, we have calculated the net force towards the center of curvature C1 was this value sigma 1 ds1 ds2 t by r1. So that was sigma 1 ds1 ds2 t by r1, and due to sigma 2 we determine plus, that is this value, so plus sigma 2 ds1 ds2 t by r2. So these two are the net force due to the stresses sigma 1 and sigma 2, which is opposite to this direction, that is the pressure force is acting outward from the center of curvature. Now we have determined this rate force is nothing but summation of these two, this one, that rate force is nothing but the summation of these two, which is completely opposite to the pressure force. So at equilibrium these two will be balanced. So at equilibrium, what will be the condition? At equilibrium this must be equal with P ds1 ds2. So what we will get? ds1 ds2 cancelled, so sigma 1 t by r1 plus sigma 2 t by r2 is P. That is sigma 1 by r1 plus sigma 2 by r2 is P by T. So this is the equation of statics for any thin walled pressure vessel. So this is the equation of statics for any thin walled pressure vessel. What is the equation? Sigma 1 by r1 plus sigma 2 by r2 is P by T. So this is the equation of statics, because we got this from equation of equilibrium or equation of statics. Now we have already mentioned what is sigma 1, sigma 2. Sigma 1 is longitudinal stress, sigma 2 is circumferential or hoof stress, r1 is radius of curvature along longitudinal direction, r2 is radius of curvature along circumferential direction, P is internal pressure, T is the thickness of the vessel. Now how many unknowns are there? P is known, P is known, T is known, and r1 r2 are known parameters. These are known parameters. But what are the unknowns here? That is sigma 1 and sigma 2. Now how many equation is there? This is only one equation and two unknowns. So this is a statically indeterminate problem. So this is statically indeterminate. So this is statically indeterminate. So to solve sigma 1 and sigma 2, we have to apply boundary condition based on the situation. Now let us take first an example of spherical vessel. When the vessel is spherical. So this is a spherical vessel. Now for spherical vessel, due to symmetry, R1 is equal to R2 equal to R, and sigma 1 is also equal to sigma 2 equal to sigma, due to symmetry. So this is due to symmetry. So luckily there is only one unknown because sigma 1 and sigma 2 are same. So here if we apply that equation, r1 plus sigma 2 by r2 is p by t. So that equation becomes 2 sigma by r is p by t. That is sigma is pr by 2t. So for spherical vessel, sigma 1 is equal to sigma 2 is equal to sigma is equal to pr by 2t. This is for spherical vessel. Now if we take the example of a cylindrical vessel. What is for cylindrical vessel? For a cylindrical vessel, this is sigma 1 and this is sigma 2. Now along longitudinal direction, this is a straight line. So this is a straight line, that is r1 is infinite. R1 is infinite. So if we apply that equation, sigma 1 by r1 plus sigma 2 by r2 is p by t. That is sigma 1 by r1. Sigma 1 by r1 becomes 0 because r2 is infinite. So that part becomes 0. And sigma and r2, what is r2 here? R2 is nothing but radius of curvature along circumferential direction, that is r2 is r is the radius of the cylindrical vessel. That is equation becomes sigma 2 by r is p by t. That is sigma 2 is pr by t. That is we have determined the value of circumferential stress or hoof stress for cylindrical vessel. That is always valid. Now what is the value of sigma 1? The value of sigma 1 has to be determined from boundary condition. So this has to be determined from boundary condition. From boundary condition. Now what is the boundary condition? First of all, let us consider the vessel with both end closed. Vessel with both ends closed. If both ends of the vessels are closed, then what happens? So what is my boundary condition? That is both end of the vessel is closed. That is this end is closed and that end is also closed. Now if I take a section here, and draw the isometric view, that is this is the closed end, this is the closed end, and sigma 1 is acting like this. Sigma 1 is acting like this. This is the longitudinal stress. So what is the force due to sigma 1? That is sigma 1 2 pi r into t. R is the radius of the vessel. This is the radius of the vessel and t is the thickness. That force will be balanced. Which force? That is pressure force, and pressure force will act on this. What is the value of pressure force? P pi r square. That is area is pi r square and pressure internal pressure is P. Then pressure force is P pi r square, and that should be balanced by sigma 1 2 pi r t. So this minus P pi r square is 0 at equilibrium. That is sigma 1 2 pi r t is P pi r square. That is sigma 1 becomes PR by 2t. So for both end closed vessel, both end closed cylindrical vessel, sigma 2 for cylindrical vessel is always PR by t and sigma 1 is PR by 2t. That is for both end closed. This is for both ends are closed. Now say both end open vessel. If both end open vessel, if both ends are open, if both ends open, then there will be no pressure force along horizontal direction, along vertical direction, or sigma 1 direction 1 longitudinal direction. This is open vessel. Open. Then sigma 1 2 pi RT is 0 because there is no pressure force along direction 1 or longitudinal direction, no pressure force. So sigma 1 becomes 0. So when both ends are open, sigma 1 is 0, but sigma 2 is always PR by T. Sigma 2 is PR by T, but sigma 1 is 0 if both ends are open.